Howdy, Mr. Simonian here, and today I'm going to be talking about how you can derive the equations of motion, also known as the kinematic equations, using graphs and equations and a little bit of algebra. Uh, the learning objective is to understand how we can derive the equations of motion based on some understanding about velocity time graphs, their slopes, their intercepts, and their areas. And those equations again are called the kinematic equations, which are the equations of motion when an object has constant acceleration. So just to quickly review about velocity time graphs, that, as the name suggests, it tells you about how the velocity of an object changes with time. Two really important features about velocity time graphs that you need to know to understand what we're about to do next is that the area under a velocity time graph tells you about the displacement of the object. If you have a velocity time graph and you look at the area under the graph, that is the area below the graph and above the x-axis, or above the vertical axis, I should say. That area represents the displacement of the object. It tells you how far it went uh, over that period of time that you're looking at. And because if you don't have calculus, then we can still do this with some easier areas, some basic geometry formulas like rectangles and triangles. We can find those areas using these known geometry formulas. And so for a rectangle, it's the length times width, and for a triangle, it's 1/2 the base times the height. And if you have a velocity time graph, the other thing about that graph that you might be interested in looking at is the slope of that graph. And if you look at the slope or the rise over run of a velocity time graph, that also has units, and it tells you about the acceleration of the object. It tells you about how the velocity is changing with time. So knowing that information, we can take what we've been talking about and generalize it to a situation where everything is symbolic, and that'll allow us to um, be able to use these equations of motion for any kind of situation. So the setup is that we're dealing with an object that has an initial velocity at time 0, and so I'm just going to draw a motion diagram of the object. This is one-dimensional motion, so we've got an object moving along the x-axis. I'll draw my origin, I'll draw my starting position, and I'll draw my final position. And this object, it could be anything. It could be a car, it could be a plane, it could be a train, it could be a bus. And we're drawing the object here at time t equals 0. That's our initial time or our starting time. And then we're drawing the object here at some later time t. That's just any later time into the future. You've got some object starting at the x-axis, and you've got it ending at some later point on the x-axis. And what we're saying in the problem is that the object, it has some starting velocity, some initial velocity. We don't know what that velocity is. It really could be anything. It could be positive. It could also be negative, or it could be 0. It's any starting velocity. I'm drawing it here positive, but it could be in any direction, as well as these starting and ending points could be anywhere along the x-axis. And it's reaching some final velocity, some v final. And again, we don't know, this final velocity could be anything. It could be a very large number, could be a very small number. The way that I'm setting it up, the velocity is getting larger. The object is accelerating at a positive rate, a positive constant rate. So I have an acceleration that's to the right and positive in x direction. And so that's the situation. And if we were to graph the situation that we've set up, it would look something like this on a velocity time graph. You get velocity on the vertical with units of meters per second, and you've got time on the horizontal in units of seconds. And at time t equals 0, I have my initial velocity. And at some later time t, I've went up to this final velocity. So this is where I'm starting on the graph, and this is where I'm ending on the graph. So if I want to see what my velocity time graph looks like over that period of time, I'm just going to connect the dots. And this is what my graph looks like if my acceleration remains constant over that period of time. And what we can recognize about this equation right off the bat is that if you look at the equation, or if you look at just what the graph looks like, the graph is a line. And what we know about lines is that, at least if we were in a math class, we would say that this line has the equation y equals mx plus b, where m is the slope, b is the vertical intercept, and then y, usually when you're in a math class and you're dealing with these graphs, y is the value on the vertical axis, and x is the value on the horizontal axis. So in this problem, what we're dealing with our graph is that instead of plotting y along the vertical, we're plotting the velocity along the vertical. So that's the first thing that we want to recognize, is that we're plotting the velocity on the vertical. And really, we're starting at, the velocity that we're reaching is some final velocity. So really, you could think of this as that we're plotting the final velocity at any time t. So I'm actually going to call this the final velocity. And then we've got m, which is the slope. And so on this graph, on this velocity versus time graph, the slope m is the acceleration of the object. It is the rate of change of velocity of the object. If you look on the graph, it's the rise over run, which would be your change in velocity divided by your change in time. So the slope is equal to the acceleration. So whenever we're looking at this equation, instead of writing m for the slope, we're going to interpret the slope as the acceleration. Kind of like going back to our discussion about the math conversation. When you're normally in a math class, the x is what you're plotting along the horizontal axis. But right now, we're plotting time along the horizontal axis. So instead of having x, we're going to have the variable t, which is representing how much time has passed since the object started at time t equals 0. And then the last thing that we want to look at is b. And in this equation, b represents the vertical intercept. It represents, like if you're in a math class, it represents the y-intercept. You've got some object, b is that point right there. It's the y value where you cross the y-axis. So in this case, it's, for us, b is representing the initial velocity. It's representing where the object, what the object's velocity is at time t equals 0. So instead of having b, we've got the initial velocity. And that right there is the first equation of motion that we want to have. The way that we will usually write this equation is that the final velocity is equal to the initial velocity plus the acceleration in the x direction times the time t. And this is our first kinematic equation. It tells us the velocity, the final velocity of an object at any time t if it moves with a constant acceleration during that time. This is the same equation that we've been using whenever we've been thinking about acceleration conceptually in our class. When we think about the acceleration is telling us about how much our velocity is changing in some amount of time. every time you've been answering those questions conceptually, really you've been using this equation um, kind of just in your head. So this is the math version of that equation, or this is the equation version of what you're talking about there. Having that same setup, we can look at another feature of that graph, which is the area under the graph. So taking the same graph of velocity versus time, where we're starting at time 0, going to time t, and we're starting at this beginning velocity v sub 0, or we're starting at the initial velocity, and we're ending at the final velocity. We're starting at this point, we're ending at that point. So that was our graph. The other thing that we would be really interested in knowing about is how far does the object go in some amount of time? In other words, what is the displacement of the object equal to? And we know that the displacement is equal to the area under the graph, and that area can be broken up into this rectangle and this triangle here. So we've got this area for the rectangle, and we've got this area for the triangle, and that's what our displacement is going to be. So it's going to be the area of a rectangle plus the area of a triangle, and that's going to be the length times width of the rectangle plus 1/2 base times height of the triangle. And so then we probably just want to go in there and look at and mark what those values would be. So if we're looking at the rectangle, I'm going to call this the length. And notice the length is the initial velocity of the object. And then the width is equal to the time t. The width is along the horizontal axis. It's representing how long we've traveled, how long we've traveled, and the vertical value represents the starting velocity of the object. So n for the length and the width, we've got the initial velocity times time. And then for the base of, let me do this in a different color. For the base of the triangle, notice that the base is also the time, also is a horizontal distance. It's representing how long the object has been in motion. And then we've got the height. And so we're starting at this initial velocity and we're ending up at this final velocity. So don't say that the height is the final velocity, because that would be the full height of this entire side length here. The height is the final velocity minus the initial velocity. So we've got 1/2 the base, which is the time t, times the height, which is the final velocity minus the initial velocity. Now, and remember, this is what the displacement, this is all equal to the displacement. So we need to just do a little bit of work to clean this up, but I also want us to just kind of put a star by this equation, because we're going to end up using it in a second to find out another equation. But if we're dealing with this and we're cleaning it up, we just want to distribute that 1/2 t into those parentheses there. So just kind of rewriting what we've got and distributing the 1/2 t into each of these terms. And when I do that, I'm gonna have 1/2. The first term is going to be 1/2 times t times the final velocity, but I'm just going to write it like this to keep the same order as the term I had here. And when I go in for the second multiplication, I'm going to have negative 1/2 times t times my initial velocity. And again, I'm just going to write the order like this. And the reason I wanted to do that is so I can notice that this term and this term are actually like terms, in that I have the initial velocity times time here, and I just have negative 1/2 of that same term here. So it's kind of like if you have the variable x minus 1/2 x. Because those are like terms, you can combine that as positive 1/2 x. It's the same situation here. These are like terms, so those are going to combine together, and they're going to give me a positive 1/2 of my initial velocity times time. And then I've still got this plus 1/2 of my final velocity times time. And from there, what that is looking like is I've got a common 1/2 and I've got a common t, so I can factor the 1/2 and the t out of each term. And I'm going to write it like this. I've got what I'm leaving out, which is the initial velocity and the final velocity, and I'm just going to put the 1/2 and the t on different sides. This is how the equation is usually written, or at least this is a common way that the equation's written. So I'm going to write it the same way. But this is our second equation of motion for constant acceleration. This is what we've been doing whenever we were finding the areas under graphs up till this point before we had an equation. Really, every single time you were doing this. If you went back to any of the examples we had worked in class where we were finding the area, how far an object went based on the area under the graph, if you use this equation, you get the same answer because really we were doing the same thing. And all we've done here, kind of like just what we did before, was we've come up with a general formula that will allow us to use this equation uh, to solve for the displacement of any object if it has constant acceleration, knowing this information, knowing the starting velocity, knowing the ending velocity, and knowing how long it took to go from that starting velocity to the ending. Now, I told you guys to star that form of equation 2, and we're going to use that starred form, which looks like this. We're going to use this equation, and we're going to use equation 1 to rewrite equation 2 in a slightly different way that allows us to find the displacement of the object knowing what the acceleration is. So in other words, and the way that we can do that is we want to take this first equation and we want to get time by itself. We want to get time by itself. Uh, or no, I'm sorry. I, I, I'm confusing this one with the next one. What we want to do is we want to get this. We notice that on the equation 2, we've got this final velocity minus this initial velocity. And what we want to kind of recognize is that we could get that same term out of equation 1 if I subtract the initial velocity from both sides. Then I'm going to have the final velocity minus the initial velocity equals the acceleration times time. And so now this final velocity minus the initial velocity is equal to the acceleration times time, and that's the same thing that I have here. So I'm going to go ahead and I'm going to do a substitution in, and instead of having that final velocity minus the initial velocity, instead of having to deal with that final velocity minus the initial velocity term, I'm going to go ahead and I'm going to substitute in for that the acceleration times time, because that's equal. Those are equal. Those things are the same, so I'm just going to go ahead and substitute that in. And this cleans up my equation in a very nice way, because in that very far right-hand term, I've got 1/2 t times the acceleration times the time. So I've got t times t, time. T times t is going to give me a t squared. So I'll write that last term as 1/2 the acceleration times time squared. And that is our third equation. This gives us a way to find the displacement of an object at constant acceleration at any time t, knowing what the starting velocity was and knowing its acceleration. So this is another very useful equation because sometimes you might not know what the final velocity is. You might not want to calculate the final velocity first. Sometimes it's more useful to just deal with the acceleration, the starting velocity. So this is what equation 3 is useful for, and that's what we want to have down for the third equation of motion. Now, the very last one is a special equation for situations where we don't know information about time. So if you don't know anything about time, this is the equation that's going to be helpful for us. And what we want to do is we want to combine equations 1 and 2. And whenever I write equation 2, instead of writing the 1/2 up front, I'm going to write the final velocity plus the initial velocity all divided by 2. That's just a different way of writing the equation. And it's all times the time t. And the goal here is to eliminate t. There's a t in this equation, and there's a t in this equation, and so I can eliminate that variable t by getting t by itself in this first equation, and then substituting that in to the second equation. So what I want to do is get t by itself. And the way I'm going to do that first is I'm going to subtract this initial velocity from both sides. So I'm going to have the final velocity minus the initial velocity is equal to the acceleration times time. And then the last thing to do to get the time by itself, because the acceleration is multiplied by the time, I want to undo that multiplication, which means I'm going to divide both sides by the acceleration. And that cancels the acceleration here and here. So what I have left over is that the time t is equal to the final velocity minus the initial velocity divided by the acceleration. This is what I'm going to plug into this equation because this time t is equal to this, and I can replace that there. So let's see what happens when I do that. I've still got this first term here, nothing has changed about that. But I'm going in and replacing t with this new term that I got from my first equation, the final velocity minus the initial velocity divided by the acceleration. And so what I've got on the bottom there is 2 times the acceleration. If you were to multiply the numerators together and the denominators together, what you've got is 2 times the acceleration on the bottom. So the first thing I want to do is just clean up this fraction by multiplying both sides of this equation by 2 times the acceleration. And when I do that, this 2 cancels with this 2, this acceleration cancels with this acceleration, which is very nice for us, because that means that what we've got left over is no fractions. We've got 2 times the acceleration times the displacement is equal to, and what we've got here is basically the final velocity plus the initial velocity, and this is all multiplication, right? This was multiplied by this, and there were 2 terms inside of each of those parentheses. So that's still kind of what I've got left over is the final velocity plus the initial velocity times the final velocity minus the initial velocity. And when you FOIL that out, you would multiply these 2 terms together, and you get the final velocity squared. You'd multiply these 2 terms together, and you get the negative of the final velocity times the initial velocity. You're going to multiply those 2 terms together, and you're going to get the positive of the final velocity times the initial velocity. And when you multiply those last 2 terms together, you're going to get the negative of the final velocity squared. And if you do the foiling right, which I think we did, then this term and that term are opposites. So they go away. Those basically combine to give us a 0. And then what we're left with is that 2 times the acceleration times the displacement is equal to the final velocity squared minus the initial velocity squared. And the way that we'll usually write that is by adding the final velocity to the other side. And when you do that, you get the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. That right there is the fourth and final kinematic equation. And notice that because we eliminated the variable t, this equation doesn't have the time in it. And this is really useful in weird situations where maybe you don't know the time, no time information is given. You can use this equation in those problems to hopefully get the answer that you need. So those are the four equations. That's how you can derive them. In my class, I won't be expecting you guys to derive these equations, but it's important that we know how to use them. So now that we have them, what we're going to talk about is how we can organize them, and then from there, we'll be seeing what we can do with these equations in a variety of different problems. So thank you guys so much for your time, your patience, and hope that this is making sense. If you guys have any questions, feel free to let me know. And if not, thank you so much for your time. Take care, have a good day, and I'll talk to you all soon. Bye bye.